Hi, Science 10 and Science 9. Also, Chem 11 students who may not have finished this lab. This is the video for the qualitative and quantitative observations lab. So you're going to see that lab on Teams, and you'll be filling it in based on the results that I show you just now. In chemistry, as in any science, we often wish to test ideas. We're testing hypotheses to see if they are or aren't supported by the evidence, the data that we collect. Now, when you test hypotheses, when you do investigations and experiments, there's two kinds of data, two kinds of information that you will want to collect. One is qualitative information, and two is quantitative. Qualitative information is only descriptive. It can be communicated simply with words. Qualitative descriptions might include the color of something, an observation of some kind of event happening, a sound that is made by something, the release of a gas, say in a chemical reaction in water. These are all examples of qualitative observations. Quantitative observations, always you can attach a number to them. You're not just saying, for example, it got hotter, the solution got hotter. That would be qualitative. If you are measuring the temperature, say in degrees Celsius, that is quantitative. Quantitative observations can have a number attached to them, and this makes them much more valuable, much more useful for investigations in chemistry and in any science. Now, we're going to look today at 3 different experiments. There might not be a reaction every time. We'll see what's going to happen. The experiments are adding zinc to water, adding calcium to water, and then combining one compound with an element. The compound is copper chloride, and we're going to put aluminum in copper chloride. So let's have a look first of all at the kind of observations we're going to be expected to take. Of course, I'm going to expect you to read the lab and see what I did, see the procedures, but here are the observations that I would have us write on the board if I was doing this with you as a class. In part A, here, I'm going to be interested in what's the temperature before I start the reaction, or before I add the things that can react or might react. What is the temperature during that reaction? Maybe what's the peak temperature, the highest one? Color is qualitative. What color am I interested in? What color am I observing? Color before and color during, or what color change might happen during the reaction. Gas accumulation is a qualitative, descriptive concept. You can say that it's accumulating or not, but actually at the same time, this is kind of cool, you can attach something quantitative to it. If you don't just say a gas was made, but instead say, I made this much of it in this much time, that becomes quantitative. In part B, I have the same kinds of results that we're going to report. Temperature before, during, color before, any color change that happens when we add the phenolphthalein, the indicator, and any gas that might accumulate. Lastly, copper chloride plus, it's in a solution plus aluminum. What's the color before? What's the temperature before? What kind of changes do we see? Maybe we could look at the relationship between temperature and time. I could make a little data table right here. And what's the color after? I'm going to show you the ingredients. Chemistry is a lot like cooking. Here they are for part A. How am I going to do this? This is zinc metal. You might want to make some observations about what this looks like. Science 9, this is a typical metal. This is hard, malleable, shiny, things you might think about in your observations for this lab. Here we are. That's what it is. for this reaction, here is what I have. It's going to happen on this piece of paper, well, in a beaker. I have a graduated cylinder full of water. I have 300 milliliters of water in a large beaker, and I have the zinc. Part 2 is calcium and water. Notice for both of these I have a thermometer. This is not working out so well. That's what I want. I have a thermometer, and I have calcium, which you can see as this crusty material right here. This stuff is very hard. It will only break with a hammer. The other things you might have noticed about it is you might want to go back and pause the video and make some observations about what does the calcium look like. That might be qualitative. Let's get these on. For part 2, as you can see, I hope with I'm angling the camera right, I have the following: 150 milliliters of water, an Erlenmeyer flask. I've got 6.52 grams of copper chloride, and I'll show you that more up close in a moment, and 0.75 grams of aluminum foil. This is the copper chloride ingredient. I hope I'm focusing the camera right. I have a thermometer for this one as well. We're going to see what happens. Let's have a closer look at the crystals there. These are the crystals of the copper chloride. I'm going to make a solution. You may remember that in a solution, there is a substance that's dissolved in some other substance. It's a mixture. Seawater is a solution, so is sugar water. But anytime you dissolve a chemical, like an ionic compound, in water or something else, you're making a solution, a liquid solution. Let's look at the first reaction. Please do read the directions, so it'll look a little bit what I'm doing. I'm going to try to focus the camera right here, there. Okay, not perfect, but not bad. I flipped the graduated cylinder, so there's a continuous column of water right here inside the beaker. Also notice, I haven't put the zinc in yet, so there's no reaction. But let's not forget temperature. I'm going to put the thermometer. I'm going to do the same thing with this other beaker right here. There. Also, in both of these beakers, I'm going to add some phenolphthalein. That is this liquid right here, phenolphthalein. Kind of hard to spell. There it is. That's also part of the method section. I'm going to use a dropper to get that phenolphthalein. I want you to pay attention to color here. And I'm doing the same thing with the other solution. Also, notice I'm putting a thermometer in here. I'll report the temperatures to you once they've stabilized. While the temperatures are stabilizing, I'm just going to shift this backwards so we have lots of space. I'm going to shift also the camera so it's viewing what happens over here. This is the copper chloride and aluminum reaction that I'm getting ready for here. Here is my 150 milliliters of water. You want to add the solvent, the thing that will do the dissolving first. into the Erlenmeyer flask. There we are, 150 milliliters of water, about. And now I'm going to add my copper chloride. Carefully, I don't spill any. Copper chloride is slightly toxic. It's not very good for the environment. The good thing about an Erlenmeyer flask is it's hard to spill it. Look at this. The crystals were a kind of blue-green, and I put this into a solution. I made this very pleasantly colored solution. Color is a qualitative variable, isn't it? Now I'm putting this thermometer in. We will get the temperature before the reaction. I'm going to get some stuff out of the way. Let's try and stir this a little bit here. There. So a slightly cloudy solution. That suggests that maybe not all the copper chloride is dissolving. Let's go back to these reactions here. We're going to start with zinc plus water. I'm going to put the zinc so it is directly below the graduated cylinder. Any gas that was made in this in any kind of reaction would then be captured by the graduated cylinder. And graduated cylinders are pretty awesome because they measure volume. We could actually use this to measure the volume of gas that was created, if any is. I'm putting my zinc in. Good time to measure the temperature. Should have done that before. In fact, temperature is exactly 20 degrees Celsius in the zinc, and also 21 degrees Celsius, 21.5 degrees Celsius in the calcium container. That being said, I haven't added any calcium yet, so that's just a baseline temperature. All right. So I'm going to come back. I'm watching the time right now is 11:29. I'm going to be watching the temperature now and then. I added the zinc around 11:28. Okay, so we're about a minute in, maybe a bit less. Next, we're going to add the calcium. I'm going to shift this other experiment over. And there. This will allow us to see any reaction that happens involving the calcium. Calcium metal is coated in air. It reacts with the air, with the oxygen that's naturally in the air. And when that happens, it makes calcium oxide. Calcium oxide can react with the water that's naturally on your hands if your skin is slightly moist, which it should be, very slightly, have a tiny bit of water that is coming out of you. That can make a strong basic compound on your hand and can cause corrosion burns to your skin. So for this reason we use forceps. I'm going to take this now and I'm going to actually, we have soap. We have soap, good. I'm going to do a bit of a variant on this experiment. I'm adding a squirt of soap to the zinc beaker and a squirt of soap to the calcium beaker. You can think about the reason for my doing that as we go along. I'm also going to start up the Bunsen burner. That's not part of the experiment, but you might see that it will become a little bit useful and relevant later on. Hey, by the way, after 2 minutes now, there is no gas that's been created in the zinc beaker. There. I've just added the calcium to the beaker with water. Let's look for a color change and the gas produced. The time is 11:31. No gas is being produced in the zinc beaker, and the temperature in the zinc beaker remains at 20 degrees Celsius. The temperature in the calcium beaker is 21.5 also. But look here, look what's happening. We have a gas that's being accumulated. Okay, this is happening a little faster than I might have expected. A gas that's being accumulated in the calcium beaker also. In fact, in that short space of time since the reaction started, and maybe you could time that based on the video, in that short space of time, it's hard to say exactly how long it took. We have had total filling of the graduated cylinder. Maybe it took, from when I first mentioned it, that's how long it took for the graduated cylinder to fill up. After whatever time it's been for the zinc, there is still no gas created in the zinc, and in addition to that, there is the temperature has not changed. All right, so we have a foam being produced. This looks really nice. All right, I'm going to try something here. We can watch that continue to happen. I'm taking this and I'm going to very gently take this over here. And I'm going to turn off the lights. I'm going to try and cover this. Okay, let's see if this works. Didn't do quite what I was hoping it to. I think possibly adding the soap was maybe actually a mistake, but live and learn. I'm going to try something different now. The temperature, by the way, of this solution has now reached 23 degrees Celsius. The temperature of the zinc is stable. Let's see what happens. Okay. It's kind of happening. Kind of sort of happening. But I guess putting in the detergent was a mistake. No big deal. What did happen there, you could just see, was that some of those bubbles started to burn. We got little popping noises. That's possible to show a little bit better. I think what happened is that foam just got to be far too fine of a foam. Let's measure the temperature again. I'm going to switch the light on, switch off the Bunsen burner. The temperature in the solution is now 23.5 degrees. The temperature in the zinc beaker is still stable at 20 degrees. Gas is still being produced. All right. So I think that we're good for that. I might follow this up with another short experiment involving the calcium because it's looking like, is anything happening with the zinc? Probably not. I could show it to you, but it looks exactly the same as when we started. When we see a color change, when we see a release of gas, this should always be considered to be evidence that a chemical reaction is happening. Now let's look at the next reaction, and I'll report those temperatures periodically when I have the time. This is our solution of copper chloride. I'm going to add a measured amount of aluminum, 0.75 grams. Here we go. Notice, remember to record the color beforehand, and our temperature at the start is 21.5 degrees Celsius. All right, I'm going to push this in here a little bit, try to get some of that air out of the copper, out of the aluminum foil, and it started. The reaction is effectively instantaneous. I'll hold it up to the camera. There. Right here, you can start to see it kind of turning a little bit brown. There. It's happening really fast. We've got bubbles being produced as well. It's starting to float. And it's covered in bubbles. Why do you think it will be floating when it's covered in bubbles? Notice the color change. It's turning a kind of a coppery color, a rich brown color. We're also looking for any color change of the solution. The temperature is at 22 degrees Celsius. The temperature of the calcium solution is 24, and of the zinc solution, it's still 20, or I should say the solution with the water with the zinc in it is 20. All right, let's look here. We've still got, temperature of 22 degrees Celsius, and bubbles are still being created. If you think there might be a reaction happening, look for a color change, look for release of a gas. This is, you don't always see these things. They don't always happen. A temperature change is even stronger evidence that some kind of chemical reaction is happening. Let's look again up close at this. Copper chloride and aluminum, brown, floating foil. If you're in Chemistry 11 and you're watching this as a makeup lab, you should be thinking about what the balanced chemical equation is for this chemical reaction, because you learned that in Science 10. The temperature of this solution has now gone up to 27.5, and it's increasing fairly quickly. You can actually see the thermometer edging up. By the way, you might remember I talked about the gas accumulating. As you can see, this had the calcium. The volume of this graduated cylinder is, well, we have 50, and then there's about 15. So once it's actually completely full, the graduated cylinder would be a volume of about 65 milliliters. After the volume, in fact, you could even guess yourself how long that took based on the timestamp on the video, and when the bubbles started coming up in the solution. As soon as the bubbles started coming up in the solution, they had gone past a level that the graduated cylinder could fill. So you should actually be able to tell me exactly how long it took for the 65 milliliter graduated cylinder to fill with water, to fill with gas. The temperature of this reaction piece here with copper chloride is 30.5 degrees. The temperature in the calcium beaker is 23.5, and it's still stable at 20 degrees Celsius in the zinc. We've got bubbles here. Of course, I never collected these bubbles. I never planned on collecting them. So we don't know what the volume is. We just know that bubbles are being made. So again, at this point you should be able to give me some qualitative observations and some quantitative observations. How much gas was made? How long did it take for it to get made? What kind of temperature increase did we have? Still stirring this. Stable at 30 degrees Celsius. Consider making a comparison of the color of the copper solution now. Is it the same depth of a blue color? Has there been a change in the color of the solution? Has the blue changed? How about the foil? Compare the foil before with the foil as it is now. You can't hear it, but I can hear crackling and popping as the bubbles come to the surface. This is a more complicated reaction, but because it involves hydrogen being made, but again, chemistry 11, the single replacement reaction is something you should be able to get from this. So, for a review, you've got the temperature before, temperature during for each of these. You have color changes you will have seen. No gas was produced in the zinc beaker, but you saw how much gas was made in the calcium beaker. In other words, you have everything you need to answer this lab. I was hoping that we'd be able to, let's see, it's 26 minutes already. Well, I was hoping I'd be able to keep this video going long enough for the copper chloride to lose all its color. I can tell you from personal experience what probably won't surprise you, which is that if you leave this overnight, especially if I were to add more aluminum, eventually the blue disappears. This should lead you to think about what it is that made the solution blue in the first place. Notice that there, instead of the shiny aluminum, we have a coppery brown color. The aluminum appears to be disappearing, while the blue color of the solution also disappears. Anyone in Science 10 or Science 9 is welcome to do some research on the reaction between copper chloride and aluminum and think about what's being made. The temperature of the solution is now 33 degrees Celsius. That is everything that I was going to cover in the regular part of the lab. I would like to try something one more time, and that is I'd like to try making the gas one more time because it's kind of a fun demonstration if it works. So I think it was a mistake using the detergent. It works for other settings, but it didn't work here. For simplicity, I'm just going to add this to the beaker with the zinc in it. Clearly the zinc does nothing. It's still at 20 degrees Celsius. The temperature in the calcium beaker started to go down just a bit. Now it's at 23. Temperature in the foil is now at around 32 degrees Celsius. Maybe that's going down a little bit. I'm going to add some more calcium to this. All right, there. Again, you should be able to see, oh, you can't see because it's not properly. We've got a gas being produced. The calcium is what's doing it. You can also see the zinc in there, but the calcium is making the gas. There was phenolphthalein in here as well. We're seeing that color change again. And the vial is full. And that was really dumb of me because there was detergent in this one as well. I'll tell you what actually is supposed to happen is that if you collect this without detergent, if you do this without detergent, or if you do this in a way where you're able to collect the bubbles and not have a foam, which is difficult to burn, you get what's called a pop test. You can look this up, a pop test. Pop tests are often used in analytical chemistry to see if you've made a gas that burns. If you fill a tube with the gas and you put it up to a flame, a positive result for the pop test is it really makes a big popping or a whistling sound as the gas inside the tube burns. That's what I wanted to have happen. Totally messed up on that otherwise, but what we should be able to see if this is done correctly without foam of the solution that's hard to burn, you should be able to see a little flare as the gas burns, and you should hear a pop as the reaction happens, as a miniature explosion happens in the tube. On the positive side, same thing happened when I did it again with calcium. That's all you need to know for the qualitative and quantitative labs.